Here we are, it's the physics video lecture. Physics 2A, video lecture 26. So let's begin. We're talking about torque, we're talking about rotational dynamics. So we have a lot to do, but we'll start with torque in the equilibrium conditions, and then eventually we'll get to rolling and other rotating objects. So torque, first of all, I will remind you, is just a twisting force, and it's best discussed by talking about tightening a bolt using a wrench. Okay, so there's our wrench, there's the axis of rotation right there in the middle, and if I want to tighten, I take this force here, and because of this lever arm, I get what's called a torque. So there's a force times a lever arm gives us a twisting force. In this case, we're getting a clockwise twisting force. And this length here, R, like that. And we use the Greek letter tau is equal to FR, or R times F. And in particular, we have to use this expression, we have to have perpendicular force and this length R here, as I've drawn perpendicular. F and R are perpendicular. If they're not perpendicular, we just need the perpendicular component. I'll do another example. Suppose I were to apply my force in that direction. So that's a different force. So here we have torque is F times R, but we can only take the perpendicular component that is contributing to the torque. For example, if I decompose this vector into a parallel and a perpendicular component like this, the parallel component would just be pushing on the end of the wrench. That's not going to loosen or tighten that bolt there. Okay. So the torque is obtained from the perpendicular component. So we could also say FR sine of theta if this were the angle theta here. Okay. And that's the formalism we were using, or that came up in the homework problem. But really, if you just remember this and the fact that you need the perpendicular component, you don't have to memorize another formula. Okay? You can always find the perpendicular component and do it that way. Good. And the units are newtons times meters. So there is our torque. And we could do a couple more examples, but we had a couple on the homework already. So the next point to talk about is equilibrium. So up until now, we thought, well, if the net force on an object is equal to 0, then it's in equilibrium, okay? Or constant state of motion. But if an object is at rest, net force equals 0, then we have equilibrium. So that first condition, net force equals 0, is still going to hold true, but there's a detail here. So I have a bicycle wheel that I'm going to use for various demonstrations, right? It rotates about an axis. That's nice. It's also really massive. I think it's been filled with some kind of cement up here in the inner tube. Okay, some kind of really solid type. Here's the thing. Equilibrium right now, as long as this thing doesn't rotate on us. Okay, at a point where it's balanced. Good. So it's in equilibrium. Can't get this thing to play along. Good enough. It's at rest, and what is the net force on it? The net force is the weight and then the force of this frame holding it up. We can say a normal force and a weight again. But if I add two forces to it, one in this up direction and one in this down direction, like these pens here, those two forces are going to be adding up to 0 as well, because one, up plus down equals 0. Okay. On the other hand, if I apply these forces to this wheel, it's going to rotate. Pull up on one side and push down on the others, just like with a steering wheel. Okay, you can do equal forces in opposite directions. Those net forces are 0, but we're rotating. So these forces that I just explained right here, they provide a torque to the wheel, just like in that homework problem we did. So our next equilibrium condition, in order to make this complete, is that the net torque also has to be 0. So net force equals 0, that's something we already knew about. Net torque equals 0, and then something, an extended object can really be said to be at rest. Okay, the net force and the net torque equals 0. So we'll do an example. And I'll add one more convention as a note here. Your counterclockwise torque is positive. So your clockwise would be get the minus sign, your counterclockwise would get the plus sign when we're setting problems up. So let's do these examples that we had started last time. So we're going to take a meter stick or just some kind of uniform rod and balance it on this pivot here, on this point. We want to balance this thing, and we know that the weight acts at the center of mass that I always draw with a little star, and so we have mg acting right there, and we have to balance this with another m, and then we have mg acting right there. Okay. So what are the torques? Now the torque can be measured from any point you want to. And typically, we like to measure it right with respect to, or I should say right here, with respect to the obvious pivot. But we can actually measure it from anywhere. And we're going to do this problem measuring it from two different places. So this thing is on a support, and it's balanced. The stick has a mass, lowercase m. The weight there that we're hanging from the end, uppercase M. And we'll say we have a uniform stick of mass M, comma, length capital L. Okay. So we also have here a normal force, right? So F net equals 0, we would be saying minus mg plus n minus lowercase mg equals 0. That would be the net force equals 0 in y direction. That's all we have. So there's one equation for us. Now, the net torque equals 0. There are two ways to do this. Okay. The first way is to take this as the pivot, and now I'll measure a length x. And then what would this length right here be? Well, it's half the length of the stick minus x. So I would have L divided by 2 minus x right there. So one way to do these torques would be to say this counterclockwise torque, we can say mgx minus mg lowercase L over 2 minus x equals 0. That would be one way to get the net torque to be equal to 0. So that's a force times a lever arm. I'll just kind of draw that. Force times the lever arm here, and here I have the force times the lever arm there. So that's setting up a torque equation. Force times length minus this force times that length. And of course, we could set that up and solve for one unknown. The other way to solve it would be to choose this here as the pivot. In other words, the end point. And that's important to talk about as well, because this force will have no lever arm if we choose this to be the axis of rotation here. Okay. It has no lever arm, and then we have or. So these are equivalent, not to be used at the same time. The equivalent one is N times X, normal force times X, that's a torque. Okay. And the other one would be clockwise, so minus mg. And now the entire length from the end to the middle of the stick is just L over 2. L over 2 equals 0. So this is very important, it's or. You can use this equation or this one, because this is a different axis. Okay. This was from, I'll call this the point A, and this is the point B. So if I choose A as the axis, I get this one. B as the axis, I get that one. Okay, so that's the balanced stick in all its glory. But let's even do a simpler version of this just to make sure we don't get confused. Actually, you know what? Since x is an unknown up there, or just general, how about we solve this equation here for x first? Okay. So solve for x. So we have capital mgx minus mg L over 2 minus a negative plus mgx is equal to 0. Okay, so we have x, and by the way, the g's we can get rid of right away, they're common here. So we have x times lowercase plus uppercase m is equal to m times L divided by 2, bringing this to the other side. So x m divided by m plus capital M times L divided by 2. So here's an interesting result. This is very general, 2 different masses, and where you balance the thing. So just to make sure we check this result, check for lowercase m equals uppercase m. Okay. If lowercase and uppercase m are the same, then I have m over 2m, okay, and x equals L over 4, and x equals L over 4. Now this is an important result, because what that means, we're balancing this stick. Star is right in the middle, okay? And of course, this is L over 2 is the right half of the stick and the left half as well. And apparently we're saying that if we have mg here and mg here, this is the center point. See, this is the center point of that half of the stick because the weight acts at the center of mass. A really common mistake that beginners make is to set up a torque equation. Imagine the mass of the stick is all here at the end, okay? The end has nothing to do with anything. Center of mass is in the middle. That's where the weight acts. And so this is the natural teeter-totter balance that you would have. Say you had a teeter-totter and you had equal masses at either ends, right? That would be the natural balance. Okay, so you can have a lot of fun with these torque equations. Let's see how we're doing time-wise. 16, fantastic. I'm going to set up one more problem that is the one that was always done in our lab. Now, the online labs probably aren't going to feature the same thing, but it's a good one nonetheless. And oh, that picture's good, so I'll go ahead and erase this. And then we'll assign a couple more equilibrium problems. They're useful. Good. So this next example, this is how we set it up in our lab. We had meter sticks with a bunch of little holes in them so that we could put them onto a stand with a pin there. And of course, if this is a pin or an axle here, then if you let go of this thing, it'll just swing. Okay, it'll swing back and forth. Got it on a pin here and it's free to swing. So what we then do is take a string, another hole here, and hang a weight off the end. Okay. And I'm going to start numbering these things 1, 2, and 3, but I'll go ahead and put the center of mass in the middle of the stick, and we know we have mg there. And just to make it more tricky, we hang more than one mass from here. I'm not going to do that on this problem because it just adds a bunch of torques. But yeah, I can hang masses from different places here. And you see those, this one, of course, we know is there because it's the center of mass of the stick. Okay. But the analysis of the forces as we have them, we have a tension here, and I'll just call this M1. So we have a tension here in the string due to hanging the mass off the pulley. And there's a certain angle that the string makes with the horizontal. And then the pin here is holding this up as well. So the pin provides a horizontal force and a vertical force, okay? Because this force to the right, this vector here has a horizontal component, and that's going to be opposed by this one. So I call this R sub x, and this R sub y reaction force, but it's just the force from the pin, has two components, mg, the weight of the stick, and then this tension. So that's the full set of forces. And we'll go ahead and take this, as I've labeled it, as the axis. So now we'll just set up our equilibrium conditions. Okay. So we have forces in x direction. We have minus Rx plus The only other one is T cos theta. And we have, for Fy, we have Ry, we have minus mg, and then we have plus T sine theta over here. Tension sine theta, and those are both equal to 0. Now, I have to say something about the tension. It's clearly equal to M1G. Okay, so tension is just M1G, whatever I hung off the end there. So those are our force equilibrium conditions. What about the torque? So the torque we'll go ahead and measure from this point here, and neither Rx nor Ry contribute any torque because they're acting right on and parallel with the axis. Or right on the axis without a lever arm, we'll just put it that way. No lever arm here. So the torque, the clockwise one, we have minus mg times the half the length of the stick. Clockwise gets a minus sign, plus the counterclockwise one is T times the entire length of the stick L. So this is our torque equation. These are our, I'll go ahead and box them right here. These are our two force equations. So yeah, let's see what we have here. We have three equations. We can conceivably get three unknowns. For example, R sub x and R sub y are not known. And the idea where we take a known stick and hang it up here with a known weight. So R sub x and R sub y, now T we can say is known because we had to hang a weight off there, so we get R sub x right away, T cos theta. Then we get R sub y mg plus T sine theta off of this equation. Those equations there. Oh, here's a mistake. T mg over L torque. Yeah, torque was this lever arm L over 2. This lever arm L, but it had T sine theta. So good to catch these mistakes, right? T sine theta times L equals 0. Okay. So yeah, there's an example that relates all three of these quantities. Two equilibrium conditions for the force, equilibrium condition for the torque, and you have three equations you can solve for three unknowns. Okay, good. So like I said, the old lab manual had this meter stick with other masses hanging from it. They just add terms to here. Conceptually, there's no difference. Okay, so that I think is enough for statics. And I will assign one or two more statics problems. There's some good ones in the book. And I think we already did one. Good. So that's how it's done. And I'll stress once again, you could choose any point, actually anywhere, but any point in the vicinity of this stick as that axis about which you measure the torque. So I chose this one because it got rid of two forces right away. But you can choose any point as the axis and get the same answer. There's a proof for that. I sometimes give it. It's not difficult, but I'll just state this as a law. Good. Now let's go from statics back to dynamics, so motion. And I brought some objects that move here, so we'll demonstrate that at the right moment. Okay, yeah. So statics we just checked off. I'll say a couple more words about it. Namely, engineers, construction engineers have to take a couple semesters of statics because it's very important for making sure things don't fall down. Okay? But we just are doing the basic for an extended object, you know, to make sure the net force is 0 and the net torque is 0. So again, we can just summarize that. Some of the force levels, right? Net force equals 0 and net torque equals 0. Because that's pretty compact, right? Those are the conditions of equilibrium. And tau net about any axis that you choose. It'll still be consistent. So back to rotational dynamics. We saw the other day that as soon as you have an extended object, the mass distribution makes a huge difference. These are the total convincers, and usually if I have people in class, we can all or some of us try them out, but if the mass, the great concentration is here in the center, and here it's towards the outside, right, the metallic part. And you can just twirl this really rapidly. Here you just feel a much greater resistance, okay, because there's more mass further away. If you've ever picked up a big long 2x4 and tried to carry it across your shoulder, or a ladder or something like that, you'll also get that feel that you cannot twist your body very rapidly. Since you don't have these special devices, if you do have a meter stick, even a short wooden ruler would work, but if you have a stick or a meter stick or something, this twisting action is much easier than if we have our hands, if we have all the mass extended to one side, much more difficult. So try that out to get a feel for rotational inertia. So the first thing we have is rotational inertia, and that's also called moment of inertia. Actually, it's primarily called moment of inertia, but rotational inertia is the right way to think about it, because it's resistant to the rotational state. Moment of inertia, get the letter I, and it is the sum of the masses times their length, their distance from the axis of rotation squared. You sum over every mass and its distance from the axis of rotation squared. And there are interesting consequences to that. So, actually, I think I'm going to show these first. So one consequence is seen with rolling objects. So we're going to do some rolling races. Rolling races down this incline here. That should all be visible, hope so. Bring this a little closer. Okay, good, I think this is visible. Yeah, we're gonna race things down. Now the first one is a metal hoop versus a wooden disc, and they have the same weight, okay? Now this one has all the mass concentrated on the rim, and this one has a different mass concentration. Now, let's go ahead and write down what we have here. So moments of inertia, I'm going to make a table right away. The simplest one is a hoop, because all of the masses are the same distance away from the center, namely the radius of the hoop. Okay, so this one we can immediately write down moment of inertia as mr squared. On the other hand, the disk, which is filled in, okay, with a uniform mass, it clearly has a smaller moment of inertia because all of the mass is not concentrated at the rim, right? It goes all the way from the outside to the center. So all of these L sub I squareds are not the entire R. So it's less, and it turns out a calculation that we don't have to do shows that it actually has 1/2 the moment of inertia. And for the record, the moment of inertia of a sphere, a uniform sphere, is 2/5 mr squared. Okay, and 2/5 is a little bit less than 1/2. Okay, so this one has the smallest, this one has the greatest moment of inertia. So which one rolls faster? This is a race. You guys have to put your bets down before I let go. Which one gets to the bottom of the ramp first? The disc or the hoop? Okay, let's have a look. On your marks, get set. The disc. Okay. Once again, the disc versus the hoop. Okay. Disc is rolling much faster. A related example is these two wooden discs. They've had steel plugs put in them, and I think you can see that. And on this one, the steel plugs are towards the outside. Here, they're towards the inside. So which one has the greatest moment of inertia? This one has more mass with greater L, right? More of the mass is out towards the outside. So this one has a greater moment of inertia. Which one's going to win the race? Okay. This one you should be able to call. Both red. All right. And this one has the moment of inertia, smaller one, because the masses are closer. And once again, mark, get set. Okay. It also rolls much faster. Now, to make a fair race with spheres and discs, you'd want them to be a similar radius. So here's a sphere and here's a disc. Now the sphere has a slightly smaller moment of inertia than the disc. Okay. I shouldn't actually do this before I'll do the hoop. Okay. Sphere versus hoop. Because it's going to be, here we'll go. See what happens. On your mark, get set. Sphere's the clear winner. Now I'm going to go to the disc and the sphere, and it should be a closer race. Slightly closer race. Let's do it again, so I'm not in the way. Okay, good. So we have a bunch of those, but let that be enough. Actually, we used to have, I forget. Okay, those were the rolling races. Now, how do we explain them? How do we explain them? Actually, before I explain it, I'll do one more rolling race. This one's interesting because we have these wheels And the axis of rotation, or the axle on which it rotates, has a much smaller radius, so it slows down the action. Okay, so it's not over so fast. So maybe this is a good one for us to do as well. Okay, and the thing is, this time we have two equal masses, and the holes have been drilled out on the outside and on the inside. So which one has the greater moment of inertia? If the masses are equal, and this one has more mass on the outside, this one has less mass on the outside. Okay. So which one is going to win? Red or blue? Okay. You guys place your bets, and no one's here to control. Blue takes the lead. Fantastic. So this one slowed the action down so we could actually see it. This one has a smaller moment of inertia. Okay, so now I have to explain why that is the way it is. And I'll just put that here. Checking the time once again. Yeah, we have time for this explanation. So we're doing the rolling motion, and clearly the moment of inertia plays an interesting role. So I'm going to set up an energy equation. And we'll just draw a ramp the way we like to do. Here's the rolling race. It's down a ramp. We come out level here. That level. Try again. The inclined plane. Could we come out here? So, if we start up here at point A, and we're a height h above the bottom, and we come rolling down here to point B, I'll give it a little speed like that, okay. Then what does energy conservation tell us? Right, there's no collision happening here, and there's no friction, so energy is conserved. Actually, technically there's a rolling friction, but we're not worried about it. Okay, there's no loss of energy. Energy is conserved. So we have our good old equation, E sub A is equal to E at B, and now we have to fill in some content there. At point A, it just is mgh. Now here at point B, it's moving, but it has two kinds of kinetic energy. It has 1/2 mv squared, but it's not only moving, but it's rotating. So it's translating, that's a forward motion, and it's rotating, so it also has 1/2 I omega squared. It has two kinds of kinetic energy. And you could say the more that is stuck in here, the lower the smaller the speed is going to be, because this is what we have to work with, mgh. Okay. So let's go ahead and remember, first of all, that V is equal to omega r. So this was an important result from rotational motion, relation of linear and rotational motion. So the speed is equal to omega times the radius. And then we can write this equation as mgh equals 1/2 mv squared plus 1/2 I And now that omega can be written V divided by R. Okay, so divide both sides by R, omega is V divided by R. V divided by R squared. So this second equation I'm going to simplify for you. Now you could actually just look at this and declare victory, but let's go ahead and finish out and solve for V. So solve for the speed at the bottom of the hill, which is what that is. Solve for V, and we have, we'll do this in a couple steps, mgh equals v squared times 1/2 m plus I over 2r squared. I just factored out the v squared. I'm going to do two things. I'm going to divide by m, and multiply by 2, which is going to cancel those, and I get a nice, right, the m's are gone, I get a really nice expression. I get v is equal to root 2gh in the numerator, but it's going to be divided by something. Root 2gh divided by square root of 1 plus I over mr squared. Okay. So yeah, draw this, write this out pretty large so that you really see what's going on here. Let's talk about this for a minute. Okay, it's a big red box here. And so, got to discuss this result. Now, if you can just ignore the denominator, this is the speed that something acquires when it travels through a vertical distance h. Okay? So, you know, if we were talking about a sled on a slope or what have you, something frictionless, we would have just expected to get 2gh, root 2gh. Okay? This result we've gotten many, many times. Now, because we've got this denominator, 1 plus something, the speed, the actual speed here is slower. Okay? It's slower, and it's slower because a lot of the kinetic energy is just in the rotational component. Okay? And the way this rotational kinetic energy comes into play is that we got the 1 plus this term right here. And you can say the greater the moment of inertia is, the slower your final speed is going to be. Okay. So if you can minimize the moment of inertia by putting all of the mass in the center and just having a very light hoop on the outside, then you can get the maximum speed. So yeah, this is what energy gave us. So next time we're going to do rotational dynamics in terms of Newton's law. But you see, the energy, conservation of energy is a really powerful concept. And we were able to use this right away. Remember, we got these expressions, we got the expressions for the moment of inertia when we were talking about kinetic energy of a rotating body. And so that's what we put into here. Okay, so this is worthy of a few notes. V is less than the case where moment of inertia equals 0. When we were talking about sliding objects, there was no rotation. We didn't need any rotational kinetic energy. So where kinetic energy of rotation is 0. Okay, good. Do I have time to give you a homework? Must give you a homework assignment. And what was this? 26. So homework 26. We're in chapter 8. And let's see how far we got. did 27, that was already a pretty good one. Let's do chapter 8, 25. Chapter 8, problem 25. That's one more statics problem. And it's a little ambiguous. Just make sure you put the cable at the end of the sign. The ice cream sign, put the cable at the end, you'll see. And let's do some, they have some energy problems here. So yeah, rotational kinetic energy. Okay, here's a really good one. 52. 25 and 52. Let me say a little bit about this problem 52. Because we've had everything we need to do to solve this one on the board. But instead of asking for this, they're asking for V. So in problem 52, they tell us it is a sphere of a certain radius. So, by the way, first of all, solve it completely analytically. Don't plug any numbers in until the bitter end. Sphere, they've got a ramp with an angle. Angular speed of the sphere at the bottom if it starts from rest. So for problem 52, solve for omega. See, here I solved for V, omega at the bottom of the ramp, but we know that omega R is equal to V. So that shouldn't be too hard to do, okay? And I gave you H here. They're giving you an angle and a distance, okay? But if you have an angle and a distance, of course, you can get the H. Okay, so they're giving you an angle and a distance, okay? So d sine theta is going to be the H. So everything is actually here, but go ahead and work your way through it. They told us a sphere, so all these things are going to acquire certain numbers, but at the beginning you just want to work your way through it analytically. Okay, good. That's the homework right there, and we'll see you next time.